All right. Hello, everyone, and welcome to our next session at the Future of Electrification Conference. My name is Ryan Blackwell, Marketing Specialist at Delta Q Technologies. Before we get this session started, just a reminder that it will be recorded and available to watch on demand afterwards. If you have any questions during the live session, please add them to the Q&A, which you can find at the top right corner of your screen. We'll be getting back to these and answering your questions at the end of the session. With that, I would like to introduce our next speaker, Delta Q Technologies Senior Product Manager, Mourad Chergui, who will be speaking today about the impact of electric powertrain voltage levels. Welcome, Mourad, and take it away.
Thank you, Ryan. Good morning, good afternoon, good evening, everyone. Welcome to another presentation as part of the Future of Electrification event. So before starting the presentation, I would like to talk about the motivation behind this presentation. In talks with various OEMs engaged in various stages of electrifications, that will be expanded to cover most of their product lines, we have uncovered a few things. One of them is that many of these OEMs are primarily considering three powertrain nominal voltages levels: 60 volt systems, 350, and 700 volts. We noticed that many of these OEMs are overlooking an important voltage level there for powertrains, which is considered intermediary voltages from 72 to 120 volts. Additionally, some various OEMs are considering powertrains with very unconventional voltage levels. So we saw voltages of 130 volts, 144, 150, 250, 465, and others. So there seem to be a lack of voltage level standardization with various OEMs, and that's this presentation here. We'll try to introduce a few aspects about this voltage levels. The first thing is we provide an attempt at the definitions of standard voltage levels. We'll present some of the aspects of intermediary voltages from 72 to 120 volts. We'll talk about safety and the primary source standard for safety, which is IAC 60479-1. And then we present an example of a standard that is commonly used for a consumer and professional product in terms of safety and how it evolves and what the levels of voltage is there. And we will present some of the ZAPI group intermediary voltage powertrain components, and we'll conclude with a few closing remarks. Before starting, I would like to make a disclaimer that the information presented in this session are for informational purposes only and should not be constructed as professional advice or opinion on safety or regulatory matters. So let's start with attempt at defining some standard power levels. This aligning voltage levels around standard values offer many benefits. The first one is it offers greater flexibility in terms of sourcing for commercial off-the-shelf products and components and subsystems, which means much wider availability and also lower costs instead of custom designs of subsystems. Additionally, the OEM can benefit from an extensive knowledge base and experience across various industries and sectors. And then the last one is being able to use industry best practices. So looking at the different voltages, we can define them into 5 main categories. It is what's considered low voltage, which are voltages below 60 volts. And generally for various applications, it's around 48 volt nominal levels. Then there is intermediary voltages, which spans from 72 to 120 volts. And typically these are 70 to 80 volt 96 volt nominals. Then there is another levels which I would call medium voltage, which spans from 300 to 400 volt levels to 450 volt levels, and it's considered around like a 360 volt nominal. Then we go to the much higher voltages, which could be grouped into two categories: voltages from 500 to 870 volts. That would be a 700 volt nominal, and even higher levels from 850 to 1500 volts would be a 1200 volt nominal. A little comparison about for different applications about where these voltages could be used. So these five categories here, this is an attempt to actually provide where what levels could suit for every application. So looking at the low voltages below 60 volts, they are suitable for applications with typically nominal power that is less than 20 to 25 kilowatts. The benefit of this is that it doesn't, from a safety point of view, it doesn't require uh, any protection, and it's using common MOSFET technologies that are very widely available, and the components to build a powertrain are widely available from various vendors, which means that wider availability and also lower costs. This type of powertrains could take charging up to 22 kilowatts. And there is an additional benefit of lower voltages is that the vehicle can be maintained and repaired in regular service shops. That's not true for the higher voltage systems, which would require trained, very specialized AV equipment to be available. The intermediary voltages that spans from 72 to 120 volts offer similar benefits to the lower voltages, but like there should be more safety protection available there to protect people. The components are also widely available, and it allows charging up to 22 kilowatt. When we go to higher voltages, the next standard voltage is 360 volt nominal, and that's this voltage level is stemming from primarily from the automotive industry that is use it quite extensively for battery powered electric vehicles. So there is availability in the component. Unfortunately, most of the components available are custom and available for the automotive industry. There is lesser limited availability for standard equipment for other industries and small scale production. 360 volts allow fast charging up to 43 kilowatts, and also it could be used super fast charging up to 150 kilowatts, although that charging at higher than 50 kilowatts would require cooling the plugs and then the wires. Then we'll go to the higher voltages, which where most of the industry, including automotive, is turning to, which is the 700 volt level. Like we have seen many cars in the that are being used with the 700 volt nominals. So there are more and more technologies and uh, either IGBTs, standard IGBTs, or silicon carbide technologies to support this type of voltages. The systems are still in very limited availability, so there is not a lot of flexibility, and there are some challenges that need to be overcome in terms of insulation and safety system. But the advantage of this that they can offer super fast charging up to 250 kilowatts without needing cooling the cables and the plugs, which would allow like 15 or 20 minute charging, super charging. And then there is an emerging field for 1200 volt nominal systems. It's still in the emerging phase, but one of the sole benefit is it will allow super fast charging up to 350 kilowatts or even more. So this is a little bit comparison about the different voltages. Uh, I'm pretty sure that most people attending the session are familiar with the benefit of using below 60 volt powertrains. So they offer many safety advantages because the voltages are considered touch safe, so that it allow to design systems that are cost effective and simple design. And this type of power levels of voltage levels would allow up to approximately 25 kilowatt nominal power on the vehicle. Anything more than that would probably require higher voltage levels. And one of the biggest advantage, besides actually lowering the cost of the total system, is that they could be maintained in regular service shops. Let's have a look a little bit about the intermediary voltages that is often overlooked by many OEMs, and that's voltages from 72 to 120 volts. They have been used for many decades in various AV applications. They would offer the ideal voltage range for compact to mid-size vehicles in the 20 to 75 kilowatt nominal power. They avoid the cost and complexities associated with higher voltages, 350 to 1200 volts, by employing common MOSFET technology that is very available and cost effective in the industry. It avoids using reinforced electric protection and therefore enabling simpler and cheaper systems. It bypasses the use of high voltage interlock loops, HVIL circuits that are not needed for these power levels. And the OEM can source a variety of components for on-road, non-road applications, which means that they can provide very cost-effective solutions. Let's have a look at some of the systems that already exist that are in these voltage levels. So from on-road vehicles, this product is used for many consumer and uh, professional applications such as light commercial vehicles or motorcycles or off-road vehicles, UTVs. And this program provide a range of nominal product going from 10 kilowatts to 60 kilowatts of nominal power on the vehicle, and the battery voltage range from 72 to 100 kilowatts, and you can have some fairly big packs being charged on these vehicles up to 30 kilowatt hours. In another side, for no-road mobile machinery, uh, voltages from 72 to 120 volts is used in many industries. Some of the one that are actually very widely used is the articulating booms that are typically 72 to 96 volt, and the installed power is 20 kilowatt. We are seeing multiple tractors, compact tractors, being converted to 84 or 96 volt systems. Um, GSE, ground support equipment, is also while when electrifying many of the equipment, they are standardizing around 80 volts, and then the batteries could be fairly big, reaching 600 or 800 amp hours. Counterbalance trucks, forklifts, is also an industry where 80 volts is predominant in the industry, and uh, the traction power could get to like 36 or even 40 kilowatt power, and then the batteries are fairly sizable, going to 700 and even to up to 1200 amp hours. It's quite big systems. So those are the forklifts used indoors, but also for outdoor applications. Many vendors are opted for 120 volt systems, and then the bottom line, the bottom row shows various applications that range in power from up to 45 kilos or up to 62 kilowatts with very sizable batteries up to 1800 amp hours. So the intermediate voltages are used across in industries, and their performance is proven in the field. So why would someone consider the intermediary voltages? One of the biggest advantages is actually cost. There was a study that was done by one of the OEMs producing no-road mobile machinery. And the study concentrated around electrifying a front wheel loader. So it's a 5.7 ton operating weight. The traction force needed was about 50 kilonewtons, and the max speed sought for this vehicle about 20 kilowatt per hour. So the OEM have done a comparison producing a vehicle with 96 volt powertrain and also with 350 volt powertrain. And you can see the choice of motors, currents, batteries, inverters that are used in this application and the currents involved. Yes, the 96 volt use bigger, more copper for cables, but there are also some advantages for with that. So on the overall performance, the 350 volt system is able to achieve 20 kilometer per hour, while the 96 volt is achieve 16 kilometer per hour. So it's not up to that. It's not up to the same level, but it's workable. But the biggest advantage of a 96 volt powered system is that it's 5 to 8% cheaper to produce than a 350 volt wheel loader. And on the total cost of ownership, the 96 volt system would have probably 6% better total cost of ownership compared to an ICE, compared to combustion engine vehicle, while the 350 volt would generate about 3.5% saving on the total cost of ownership. So big advantage there for the OEM producing cheaper machines, and also for the user getting better total cost of ownership. And that's the advantage of using one of the biggest advantage of using intermediary voltages rather than going to the higher voltages. Um, we look at a standard 6479-1, which is actually the primary source on electricity hazards to human, to understand a little bit what are the, from a safety point of view, what are the effects of currents on people. IEC 6479 provide the basic guidance on the effect of electrical shocks on human beings and livestock. This is the primary safety standard that is intended to be used by other technical committees for preparation of standards. And if you look at any safety standard that relate to the electrical effects on human, you will find that they will the information there will trace back to IEC 6479. So it's the mother of standards when in terms of electrical effects. And so we can derive some information from that and understand what are the effects of electricity on people. So if when somebody is exposed to actually higher voltage DC or AC, anything that's technically above 30 volt can have some potential hazards and cause involuntary muscle reaction. But it's important to understand that the degree of danger to the victim is a function of the current flow through the body, which part of the body it goes through, and then also the duration of the current flow. So the voltages themselves are not that important directly, but it's what's important is the magnitude of the current and the duration, the flow in the body. And we look at some of these aspects a little bit more closer. Before going there, it's worth mentioning that in general, DC current are much less dangerous than AC current by a factor 3 to 5 times. And why is that? It's because AC produces extended muscle contraction, which freezes the hand to the power source. So that's what's called immobilization. While DC does not have that. DC was a single contraction, which usually forces the hand away from the power source. While AC, if you touch something that's AC powered, you may be immobilized and unable to remove your hand. AC power can cause a high rate of heart fibrillation and uh, and once the power is removed, the heart may not restart. While DC makes heart still, but once the power is removed, the heart can restart. And this information is actually derived from the safety standard. There is another effect which is actually called the let go of part gripped, more difficult with AC systems versus DC systems. And actually looking at statistics across the industry, accidents with DC systems are much less frequent than would be expected from a number of the DC applications. Fatal electrical accidents occur only under very extreme and unfavorable conditions. For example, in mining. Some of the aspects actually of electrical shocks would be the level of perception and reaction, which is which is the involuntary muscular contraction of the person. There are also two aspects, which one of them is the let go current, which is the current that is just enough to cause involuntary contraction of the muscle, such as inability to let go from the AC source. Immobilization is another effect that the current have the body when it cannot move involuntarily. So the AC current interfere with the nerve signals to to not allow the person to actually move their hand, and that's what one of the dangers of electrical shock. But actually, the real hazard that caused that it would be ventricular fibrillation. With the current flowing through the body, it may cause fibrillation of the heart. And ventricular fibrillation is when the human heart is in danger of failure to function. There are other effects of electrical shocks. For example, the muscular contraction, rise in blood pressure, disturbance or formation of conduction of cardiac impulses. There are maybe also other effects, secondary effect, that if the contact is very long, and that may cause deep seated burns or internal injuries or surface burns on the skin. And the higher voltages may not cause ventilation, but they could cause other forms of cardiac arrest, but this is not have not been confirmed with sufficient data. uh, Let's look a little bit more closely at some of the current and physiological effects. From the standard IAC 6479, it defined zones where the DC could see here in this diagram. It depends on the magnitude of the magnitude of the current and the duration, and it's distributed in different zones depending on the length of and magnitude of the current. So there is a DC1, DC2, DC3, DC4. DC1, 2, 3 are usually not lethal. So when it goes to DC4, is that where there is a risk of fibrillation. And you can see from this diagram that there are some threshold here of 2 milliamps, which is the threshold of perception, and then 25 milliamps, which is the threshold of detection, and then there is 135 milliamps, which is threshold for fibrillation. And the table here, table 13, provide more details about these different levels. So it is worth noting that ventricular defibrillation happen if the currents are more than 500 milliamps and not stopped within 20 milliseconds. So you could have actually a high current, but if it stopped within a short time, it won't cause fibrillation. The risks are when it's not stopped within a short time. The also the standard present also another set of data which is related to the resistance of the human body, and you can see from this table the resistance decreases as the voltage increase. So that's why actually the more the voltage, there is more possibility of current flowing through the body and causing harm. Taking into consideration the previous table and this table, we can infer, we can extrapolate the result to actually get some information about the level of harm that could be caused by electrical voltages. So 60 volt is considered as touch safe, and a limit of human perception is about 25 milliamps. Up to 120 volts, and that's why these numbers here, we have 60 volt, we have 120 volts, we have 400 volts, and we have the higher voltages. So up to 120 volts, there is no need to interrupt the current. Like the person may feel pain, but it's not that the shock is not lethal. The shock becomes lethal when the voltages are above 400 volts and there is no interruption mechanism. So from 120 to 400 volts, there could be current, but it will be safe if it's interrupted in a very short period of time, less than 20 milliseconds. For voltages above 400 volts, then the currents become very little, even for short period of time. So based on IAC 6479-1, we can make some conclusion on the hazard related to voltages. So for voltages below 60 volts, um, uh, um, 20 up to 25 milliamp current may flow, and there is no physiological effects whatsoever on the body. For 120 volt systems, uh, up to 135 milliamps current may flow through the body, but there is no organic damage or risk of ventricular fibrillation to the person. So in this case, even fault current interrupting mechanism are not necessary. For voltages from 100 volts, the body can support without being little up to 500 milliamps if it's interrupted within 20 milliseconds. So you could have lower protection in the systems that are below 400 volts with the presence of a fault current interruption mechanism in the system. For um, voltages that are more than 400 volts, um, currents higher than 500 milliamps might flow through the body, causing increasingly higher higher risks of ventricular fibrillation. So on this system, reinforced protection is necessary to avoid any contact with live parts by people. There is, I mean, we'll briefly go through a standard IEC 62368, which provide an example of voltage levels and safeguard in common consumer professional products. So this product, these standards have to do with audio and video and information and communication technology systems for both consumer and professional use. This standard have been adopted globally, and you can see here it adopted in Europe, in US, in Canada, Mexico, Japan, and other places adopting it within their regulatory framework. This standard adopt a proactive risk-based approach by identifying the hazard and testing the effectiveness of the safeguard rather than reactive incident-based perspective, um, and is based on performance testing. This product classifies energy sources and describe the safeguard against those energy sources and provide guidance on the applications and the requirement for those safeguards. These safeguards are intended to reduce the likelihood of pain injury in case of fire and also property damage. So the history of this, how this standard evolved, it evolved from previous standards that have to do with office equipment and data processing equipment, IEC 380 and IEC 4350. These two standards were merged in a very popular standard in the industry. It's called IEC 6950-1, which is related to information technology equipment. Then most recently, these IAC 6950 have been merged with IAC 6065, which is a standard related to audio and video and similar apparatus, and which both of these standards now are not used anymore. Instead, IEC 623868 is used for a variety of applications, including audio, video, information system, which is computers, and communication systems. What does this standard say? Well, it defined three levels of energy. Depending on the voltage and also the current. So it's classified source, like energy source level 1, energy source level 2, and energy source level 3, with various effect on the body. So class 1 is usually not painful but may be detected. Class 2 is painful but does not cause injury or death. Class 3 is highly dangerous. So how does this relate to protection? So with a class 1, energy class 1 level, there are no safeguard required for ordinary people. If it's a class 2, then there is a single safeguard. And for class 3 type of levels, the double or a reinforced safeguard is required. But also this standard actually identify three different type of people: ordinary people that need to be protected depending on the energy source to make everything to the level of energy class 1, where it could be safely touched by ordinary people. Instructed persons, which would be qualified as a trained worker in the facility, are allowed actually less to more access to the equipment and more access to the power source with less stringent. Skilled people, who are people who knows, who are very trained on electrical shocks, may have full access to the different board level, and this will be useful for maintenance, for example, or repair of the instrument. So you can see they define three type of levels. So similar to this standard that have been used for the audio, video, information technology, and communication systems industry, the no-road mobile machinery and the light e-mobility industries may need to get together and collectively develop and update their own safety standards and good practices for voltage levels that are 70 to 120 volts intermediary voltage, and the higher voltages 360 and 700 volt level powertrains. The ZAPI Group, as an example of a provider of powertrain components, provides several solutions for the intermediary voltages. For example, traction motors by Best Motors. So there are different systems that for 80 volts or 96 volts and scaling up to 30 kilowatts or even higher. So this is an example for induction motors. Motor controllers, they are also available in a variety of voltages, and you can see here they scale from 24 to 120 volts and provide currents extending up to 1,000 amps for controlling drives. Another component that also provided by the ZAPI group are battery chargers and provided by Delta Q and Zivan, part of the ZAPI group. And you can see here the offering that is available for charging batteries on board or off board in the 72 to 96 volts, and the power there scales from, let's say, 1 kilowatt charging up to 10 kilowatts with different product offering that are available from both companies. And now the final closing thoughts. The alignment of powertrain voltages around standardized levels offer OEMs many benefits in terms of availability of components, subsystems, know-how, and expertise and standards. The intermediary voltages 72 to 120 volts have been used for decades in various EV applications. They enable electrification of compact vehicles without incurring the costs and complexities associated with current sensing, limiting device, and double or reinforced safeguards. Commercial off-the-shelf components are much more available, and motors and controls particularly have typically lower costs than 360 volt or 700 at similar power levels. There is an abundance of safety related standards, regulation, and practices for systems that are below 60 volts. However, the industry need to get together to collectively develop its own standards and good practices for intermediary voltages, 70 to 120 volts, and higher voltages, 360 and 700 volt powertrains. And with that, we conclude this presentations, and we open the floor for questions.
Great, thank you, Mourad. So for those with questions, like Mourad mentioned, please type them in the Q&A section at the top right corner of your screen. It looks like we already have a couple that have come in here. We have this one from Jonathan. When comparing 96 volts and 350 volts, could you go into how significant the difference is in terms of charging performance? So time, heat, efficiency, stuff like that.
Yeah, thank you for the question. Good one. So yeah, the significant actual difference between 96 and 350 volts is fast charging or super fast charging. So as I mentioned earlier, as we mentioned in the presentation, with 96 volt systems, you can have chargings up to 22 kilowatts. If we want to have higher than that, for example, 50 kilowatt charging for fast charging, then you need to opt for a 350 volt systems. There is definitely a difference in terms of heat generated and efficiency. Definitely, the 350 volt systems are much more efficient. So in the vehicle, one of the advantages is you could use smaller cable or smaller wire gauges. So that means less weight and then less cost. But this advantage is counterbalanced by higher costs for installations and current limiting devices that have to be in the system. So overall, yes, 360 volts, 50 volts systems are more efficient and generate less heat, so you can have more compact equipment. But as we have shown in the total cost of ownership, a 96 volt system would be lower over the long range, and also in as a first investment for the equipment to be produced compared to a 350 volt system.
Perfect, thanks. And then we have another question. This one relates to slide 7, just asking how the voltage levels were defined. If you could go into detail on that.
Slide 7.
Yeah.
Yes. Let me go back. Yeah. So this division of the voltages, it's in line actually. Like I would refer how it evolved. It's related to safety. So I would refer to slide to this slide here. So like this is inferred from IAC 60479 to relate the current to actually voltage levels. So you can see there is a safety barrier at around 60 volts, 120 volts, and 400 volts. So below 60 volts, there is there is no necessary from a safety point of view of having protections. For systems up to 120 volts, you could have them with basic protection, and you don't need current limiting devices. Up to 400 volts, you could have systems with single protection, but if you include current limiting devices to limit the current within a specified time. In systems above 400 volts, the use of reinforced protection is mandatory. So that's where these levels are derived. It's it's from a safety consideration: 600 volts, 120 volts, 400 volts, and then above that.
Right, makes sense. We have a question from Mark, just asking if you can pull up slide 27 again.
7, sure.
Yeah.
Yes.
Okay.
You have the question?
Yeah, I think you just wanted to look back at the slide.
Yeah. So this is related to IEC 62 368-1, very widely and globally adopted standard for audio, like audio, video, information technology, like basically computer and information system communication. It's a good reference for the AV industry to look at and maybe model on that model to actually develop their own standards related to voltage levels.
Perfect. So we have a question from Mirko asking, do you know if there is a standard interface for high voltage?
Standard.
So Zappi Group has fast charger solutions for low voltage applications. Is there a standard interface like for high voltage?
For charging, yes. The AV charging have standards for sorry. So there is for high voltage, but there are some that are perhaps in development to charge at 60 volts or maybe even at 96 volts. I know like there are some in Europe, and as an example, in India, they have adopted actually a standard for charging at lower voltages, either at 96 volt or 48 volt, directly from EV charging stations. But I would welcome comments from other participants here about this question.
We have another question from Mark asking, do you know if there is a timeline on the horizon for work on any new standards?
Um, there have been some like I'm aware of some efforts there, but I believe now as electrification is becoming more and more predominant, that the industry together have to go together and push for such standards to take in place. It's in the advantage actually of the OEMs, and also on the users. Are more and more systems will be more and more electrical vehicles will be available in different type of applications. I don't know exactly the timeline, but I would encourage the participants and the companies to actually join maybe standard committees and ask for standards related to voltage levels.
Could you give an example of what basic protection equipment would look like for up to the 120 volt level?
Yeah. So basic protection would be a single barrier that protects the person from actually from touching the device. So if there is a single force. Now, double reinforced protection is you actually have to have two systems or two type of protections available for protecting the people in case the first one fail. So there is another level there that is available. So for example, let's say for example, if there is a short like a relay or something like that open, you need to have two of them. So reinforce means that two levels of protection. In case the first one fail, the other one there is to protect the user. So which means this add reinforced protection, add costs and complexity to any electrical system.
Hmm. And this kind of ties into another question. Could you kind of more specific towards material handling industry and servicing? Could you specifically say what that would look like for handling material handling devices greater than 80 volts?
Yes. So I believe in the material handling industry, especially in Europe, I believe they have kind of a they are allowed to use actually higher voltages in the 80 and 96 volt level. But let's say, for example, you have a forklift now with an 80 volt battery, so that battery is readily available. Is readily you can actually like people who are maintaining it, like they can access the batteries, they can test the things. Of course, they need to be trained, but they can access that. If it were a 360 volt system, the system would be completely sealed and only accessible by people who are trained on vehicles, like basically engineers or highly qualified technicians to be able to work on that. And even there, they need like the whole system needs to be powered off before anyone can work on it. So there are definitely advantages in having voltages below 20 volts. That from a service point of view, it does increase significantly the cost of maintenance and repair of the vehicles.
Mhm. All right. And then we have another question asking, could you touch on the voltage threshold involving an HVIL safety loop?
Yes. So HVAL safety loops are required for for the high voltage systems. I believe like in the above 120 volts. So that's absolutely required there. Typically for systems that is in the 96 or 60 volts, that is not required to the best of my understanding.
All right. If there's any more questions, please send them in. Otherwise, we'll close up this session. All right. Well, that looks like just about all the time we have for today. Thanks so much for your time, Mourad, and to everyone who was able to join us for this session. If you have any further questions, make sure to drop by our virtual booth, which is on the Accelvance platform. And this concludes today's sessions, and we'll see everyone tomorrow. Thank you.
Thank you very much.